Thanks for the opportunity to present our work here. We are Nienke and Emma from the Netherlands, from Twente and Eindhoven. And in this project, we combined our expertise on CRISPR-Cas sensing and sweat analysis to see if these two are combinable. So skin infections or pathogens on the skin are very commonly prevalent health issues globally, affecting millions of people yearly. And they can be caused by different fungi, bacteria, viruses, or parasites on top of the skin. And traditional diagnostic methods involve the harvesting of these samples from the skin, culturing, and then analysis via molecular techniques such as PCR. And usually this gives a long turnaround time, and that can be unpleasant for patients. And furthermore, there is a growing need for more specific analysis, also to reduce resistance to the therapies. And that made us wonder how we could improve this and make the turnaround time shorter. And might this be available via sweat? Because the sweat is also on top of the skin, as such as are these problems. So sweat is non-invasively and continuously available, and it's a rich composition of different biomarkers. Although it's 99% water, we can also find other stuff inside that we want to measure, like electrolytes, metabolites, antibodies, cytokines, and also body foreign stuff. But although we would like to measure these for sweat sensing applications, they could also be having negative results on the CRISPR-Cas sensing. And studies showed the presence of genetic material of specific pathogens in sweat. So that made us wonder, can we use the sweat sensing for faster turnaround times and non-invasive measurements? And would CRISPR-Cas-based biosensing be a useful tool to do this in sweat?
Yes, so many of you might be familiar with CRISPR-Cas as a gene editing tool, for which, of course, Jeanne received the Nobel Prize. However, besides gene editing, actually CRISPR-Cas can also be used for gene sensing, and that's actually where we will use it for. So the flagship protein in CRISPR sensing is Cas12a, and you see it schematically over here. And if you'd like to simplify the system as much as possible on an IEEE conference, I would say it's just an amplifier. So what happens is, as soon as a target binds to CRISPR, it can start amplifying, which actually means that it can activate thousands of reporters. So it has a natural amplification. But of course, it's also biology, so we go a little bit deeper into it. And what you then actually can see is the mechanism. So you first have the CRISPR protein, which actually has a CRISPR RNA and it's anchored to it. So you see a small 2D structure, just depicted here as a hairpin, which makes sure that the CRISPR RNA is anchored to the CRISPR. And then we have another part of the CRISPR RNA, and this is the part we can actually adapt to the target of interest. So we can make sure that CRISPR-Cas can bind to a target of interest. And then something really nice happens, because you see a structural change of the CRISPR protein. So first, the catalytic site is actually blocked, but upon the binding of a target, the catalytic site is revealed, and, well, catalysis can take place. And what type of catalysis? Well, it's actually the cleaving of single-stranded DNA. Because the double-stranded target is unwound, it actually has two single strands, so that will be cleaved first. But this catalytic site remains open. And this is the amplification reaction, because if you then add, for example, 3 or 4 quencher pairs that are separated by a small single-stranded DNA, you can follow this continuously cleavage activity as an increase in fluorescence over time. So what do these curves look like? Mostly, yes. You will mostly see an S-shaped curve if you look at CRISPR sensing papers. And that's mostly because in the beginning, all the CRISPRs are still looking for their target. Then you have the linear phase, which is the phase where, the first derivative of the linear phase. This is where all CRISPRs are actively cleaving all the reporters they can find. And then you will see flattening of the curve. Well, the linear range can directly be related to the amount of activated CRISPRs and in that way to the target DNA. So this is actually the quantitative part. And the flattening is just because at one point you run out of reporters. So the height of this curve really depends on the amount of reporters you will add. So in quantification studies, we're mostly interested in this linear range. So this looks perfect. However, besides the target DNA concentration, this slope depends on many more factors. For example, the type of CRISPR variant you will use, the CRISPR RNA and its combination. But what is especially interesting for sweat sensing is the fact that it also is highly affected by ionic strength in the presence of certain ions. And what you can see, for example, in some tests I did a while ago, is that if you, for example, decrease the sodium chloride concentration, you actually get an increase in this trans-cleavage activity, which is all at the same target concentration just because the environment changes. And also for divalent ions, it becomes even more interesting. For example, if you add manganese instead of magnesium, it becomes non-selective. It will always be active. So it's really important if we want to use it for sweat sensing to see whether, the CRISPR sensor is affected. Furthermore, other factors like temperature play a huge role because it's an enzyme. It will have a preference for a certain temperature, but maybe also other factors we didn't think of and we will face while doing sweat sensing. So this was actually our main question. What is the issue with all of these points? And will it actually enable us to do sweat sensing? Well, of course, there are many CRISPR-Cas variants, but luckily there are also some commercial available. You can just order them. So the ones that are commercial available are the LB-Cas and the S-Cas, which just originate from different bacteria. And nowadays they also have ultra variants, which are just variants that are genetically modified to perform better in gene editing. But maybe this also affects the way how they do gene sensing. In the study, we decided to go for the commercial LB variant and the ultra variant of the SCAS12a, mostly just because it was lying around. Okay, so we want to do a sweat sensing. And although in summer, when you're sporting, you might think you have plenty of sweat. Well, for studies, it's quite of a precious material. So we started with our CRISPR reaction components. So the protein, the CRISPR RNA, the fluorophore quencher, and a buffer to make sure that that's in there. And then we started playing with the amount of water and artificial sweat, just for studies in the beginning. This means that 80% of our reaction sample will be the target DNA with the water or the artificial sweat, and 20% will consist of all the components we need to perform the CRISPR reaction. And what we then see is that for increasing amounts of artificial sweat, we see decreasing trans-cleavage activity, so decreasing of this slope I talked about before. And we also see that the ultra variant of SCAS12a is much less affected than the one of LB, which can be because of it being an ultra variant, of course. But artificial sweat is interesting, but of course not the thing we're really looking for. So we also wanted to work with natural sweat. And luckily, there is a device to harvest sweat, which is the macroconduct device. Mostly it's used in the clinic to harvest sweat from babies to diagnose whether they have cystic fibrosis. I want to disclaim that we didn't use any babies. We just used one PhD student, just to disclaim. But in the end, we could use sweat in this way to see whether it also worked in real sweat. But then we saw something weird, because we saw a huge decrease in the trans-cleavage activity. So apparently something is present in real sweat that is not present in artificial sweat. Okay. But then we thought, okay, let's dilute the sample. This means that in the end we will have less target. The concentration of target, of course, remains the same in your volume, but you dilute it more, so you have less target. And let's see whether we can still sense. And then we saw an enormous restoration of this trans-cleavage activity. So although there's less target, we see much more signal. So that's interesting, because that means that we can still detect concentrations. So we also did a limit of detection study using this dilution step. And we see that although we do this dilution, we still get similar limit of detections compared to perfect buffer situations. So although we have a far lower concentration because we have to dilute, we still can get similar limit of detections as we will get in perfect buffer situations. And according to our knowledge, that's the first time that people show that you can sense in sweat with CRISPR, but it also is not that much affected. So yeah.
So that made us wonder, how can we use this knowledge? First, some future work that we could do is, of course, to enhance the performance of the CRISPR-Cas sensors, as now we used commercially available, but maybe there are better combinations. Then we can broaden the range of detectable pathogens. And even in the future, it could even be used for systemic disease detection, as there are some papers suggesting that some of the DNA and RNA ends up in sweat. And of course, then we could look at multiplexing approaches and microfluidics integration. as the Lab on a Chip's microfluidics toolbox offers some things like speed efficiency, low reagent consumption, miniaturization that CRISPR sensing needs, especially if you want to do multiplex detection, lower detection limits, and ready-to-use devices if you wanted to use it at the point of care. And with that, we like to acknowledge both our groups in Twente and Eindhoven in the Netherlands, and the funding to make this collaborative project possible. And before we would like to answer any of your questions, we also would like to